Hello everyone, welcome to another episode of Physics in the Time of Coronavirus. Hopefully by now we're pretty much in the swing of things. So let's just get started. So today's lecture number 25. We're going to be on chapter 13 still. And we're going to cover stuff that's on pages 336 to 352. For next class, no specific reading, and your homework is due Monday, right? At the same time that you would normally be going to class, or earlier. And once again, by now, by the time you're watching this, unless this uploads really quickly for some reason, you'll have hopefully scanned it in and turned it in Ben, and all of that worked okay. If not, of course, I will be understanding. So today we're going to continue talking about orbits. We'll see some more info about that and how, in fact, we can derive Kepler's laws from Newton's laws. And we're going to talk about the gravitational potential. Okay. And that means the gravitational potential energy. So, as we'll see, these types of dynamics can be recast also in terms of the energy, right? And there's advantages to looking at it that way. You know, we have in this class two basic ways of looking at things, either with Newtonian dynamics, right, talking about the momenta and forces and stuff involved and how they affect each other, and then there's dynamics according to energy, right? And in some cases, one is more useful than the other, okay? And it's maybe interesting to note that this is sort of a broad divide in physics, right? There's dynamics, right, a theory of how things change and evolve through time based on forces, and then there's a separate one derived on concepts of energy. So this is not just something that you'll see in this class, but if you take more physics classes, you'll see that things divide up in this way. Okay, so last class we ended with Kepler's laws. I'm going to switch to another color. This one looks a little faded. I bought the special refillable ones to try and be environmentally conscious or whatever, but now where do I get the refills? I don't know. Okay. So Johannes Kepler, just one P. Johannes Kepler, 70 years before Newton, found three empirical laws. So, closed orbits are elliptical with the sun at one foci. 2, we have equal areas and equal times. Right? That's a law that we'll actually derive today. We'll see where that comes from Newton's laws of gravity and considerations of angular momentum. And the square root period is proportionate to the cube of the semi-major axis. Okay, we'll also see how that derives from Newton's laws today. But first, we'll clarify a little bit about closed orbits are elliptical with the sun at one foci, right? You may think, well, okay, if closed orbits are elliptical, why even mention the word closed if there's not another option? Well, there is. There's also open orbits. So there are four types of orbits. There are elliptical, there are circular, there are hyperbolic, and there are parabolic. Right? Each of those is itself what's called a conic section, which is a special classification of shapes that have certain properties. Just realized that I have a light on in the background, and maybe that's making it difficult to see. Okay, maybe that's a little better, I don't know. So conic sections. What is a conic section? Well, we take a cone. Okay. And we take this, imaginary cone, and we take an imaginary plane and we slice it through this imaginary cone. So I would take perhaps a page of my notes, and imagine you have this cone here, and I bring that plane and I slice it through, slice it through the cone, right? And these things are both imaginary, so they can pass right through each other, right? So where that plane intersects with the surface of this cone, we call those shapes the conic section, and there are 4 of them, right? There are 4 distinct ways to slice a plane through this cone. So the first is the easiest, and that's if we take a plane and we just slice it through totally perpendicular to the long axis of the cone, and of course we get a circle. That's pretty easy to visualize, right? So this conic section is a circle, and this, of course, is a closed orbit, right? This orbit just goes around and around in the same loop, so we call it closed. And this point is the focus. Okay? Next, if we take this plane and just sort of tilt it a little bit, so now we have something like that. Imagine it's a little wider. Now we have an ellipse. Okay. So now instead of just one focus of the ellipse, we have 2 foci, there and there. Okay. This is the major axis. This is the minor axis. Should be pretty obvious. And when we talk about a semi-major or semi-minor axis, we're talking about half of this. So that would be the semi-major axis, and that would be the semi-minor axis. Ellipses are parameterized by their ellipticity, which is how far away from a circle they are, but if we take that parameter to 0, we go back to our case of the circle. The minor and major axes become the same, they become the radius, and these 2 foci move together until they overlap, and then we just have our circle with them. Okay. The next thing we might do is tilt this plane even more, such that it extends beyond the closed bit of the cone into the open bit at the end. And now there's no intersection down here, so let's get something that looks like that. What we get is a parabola. Which is a fairly familiar shape from when we were studying calculus and when we were talking about parabolic flight, right? Firing things up and then coming down. So you can think of when you fire a projectile and it follows this sort of parabolic arc, that's kind of like an open orbit, right? It doesn't complete its cycle. Maybe it could if the Earth weren't in the way, essentially, but it's following a parabolic path under that constant gravitational field. So objects out in space, right, that come in from outside the solar system, they come into the solar system, they fling around the sun once, and then they fly back out into space again, right? So our open orbits are orbits that just have one cycle, right? They come in from infinity, essentially. If we're talking about the solar system, somewhere in deep space, they fly around the sun and they get flung back out into deep space, never to come back again, right? So there was some hoobajoo and fuss a little while back about one such object that, since we have modern astronomy now, we were able to track and keep track of, and it, it had to, I don't know who amongst you might remember it, but it was very oddly shaped. So all these people were like, oh, maybe it's an alien something. Well, it was alien in the sense it was outside the solar system, but that came through our solar system, was gravitationally influenced by the sun, and it went back out. So that would be an example of an open orbit. So there's one more type of open orbit, which is if we continue tilting this plane, we get to the point where that plane is now parallel with the long axis of the cone. So let's draw that over here. And now that intersection looks like that. It's maybe getting a little busy there, but hopefully it's clear. And now what this shape looks like is this. For this one, I need to draw more lines. Okay. So, I'll put these arrows at the end just to emphasize these go off to infinity. So this is a hyperbola. And the difference between a parabola and a hyperbola is that if I go out, right, in the x direction with my parabola, I go out this way, this gets steeper and steeper and steeper and steeper and steeper, right? And then if I go over here and look way up here to see where I still have the parabola, it's going to look basically like a straight line going up. Okay? It's still following that x squared function, but as x gets larger, this gets steeper and steeper and steeper. A hyperbola, on the other hand, approaches this asymptote along the diagonal. Right? So if I went way, way, way out here for my hyperbola, right, I would just see this thing continuing to approach but never quite touch this diagonal line here. So this, excuse me, this is the other type of open orbit, right? A hyperbola, and it essentially just has a different shape. Okay? So we get these four different classifications of orbits. They are all formed by the influence of Newton's law of gravity, with a single gravitating object and a smaller object that feels that gravitational field, right? I don't think there's anything else to say about it. Okay? So for Kepler's first law, we're just concerned with the ellipse and its special case, the circle. Okay, so Kepler's second law is that one that's a little confusing to understand, that orbits sweep out equal areas and equal times, right? So if we draw an imaginary line between the sun and the planet we're talking about, and we drag that imaginary line through space, it forms an area, right? It forms a surface. So if we track the time it takes to drag out that area and calculate the area itself, then in a different point in the orbit, if we follow that object as it sweeps out that equal area, it must do that in equal time. So if it's closer to the gravitating object, right, it'll be going faster because that imaginary line will be shorter. So to sweep out that equal area, the object has to move a greater distance in the other direction, right, the tangential direction. So again, this was an empirical law that Kepler just found by observing every single night for a really, really long time the motions of all the planets and the positions of all the stars. Okay? But he didn't have any explanation for why that might be. So when Newton came along, obviously much more was understood. So now we're going to derive this law. So we have our elliptical orbit. Here we'll put the sun at one foci, right? This circle with a dot in it is the astronomical symbol for sun. And we'll say we're talking about the Earth. So we'll put a circle with a cross through it there. And then at some time later, a circle with a cross through it there. Okay. I'm going to say we're talking about infinitesimal distances and infinitesimal times, and we'll see how that leads naturally to our answer in the end, but I'm going to draw it big so you can see it, right? I mean, drawing infinitesimals as infinitesimals would mean you wouldn't be able to see anything. So we're going to say that over some infinitesimal time t, or dt rather, v dt amount of distance, right? The infinitesimal time is elapsed times the velocity of the planet at that point. And why is it at this point necessary to talk about things as an infinitesimal? Because if we took some larger time t, this v would change with time. Okay? So we now attach our imaginary line to the Earth, has some radius r, and as excuse me, as the planet moves, it sweeps out this area here. So since we're talking about an infinitesimal area, or excuse me, since we're talking about an infinitesimal time, the area will also be infinitesimal, so we'll put dA there. So that's the amount of area that's been swept out in some infinitesimal time by the Earth as it moves around the sun. Okay. So here's the clever trick. The clever trick is first we turn this into a parallelogram. Right? If this is some infinitesimal distance, then that curvy line is going to be straight over that infinitesimal distance. So we'll draw another line parallel to it over here, and then we'll draw another line, oops, draw another line parallel to it over here, not parallel to this line over there. So now what we've made is a parallelogram. So the total area of this parallelogram is going to be double the area that's being swept out, right? Because it'll be exactly half of this parallelogram. Okay. So dA equals 1/2 of now what's going to be the total area of that parallelogram. Excuse me. And one of the properties of the cross product, which we didn't mention earlier when we talked about cross products, is that if we take the cross product between two vectors, like so, and then take the absolute value of the resulting vector, so the length of that new vector, that gives us the area of the parallelogram defined by those two vectors. And you can see this easily in the case of a square, right? If we had two perpendicular vectors, right, a height and a length, well, if I took the cross product, I would just be multiplying those two numbers together. I would multiply the height times the length, and then I would just get the area of the rectangle, right, formed by those two vectors. And then that case holds when I tilt. And now that sine theta tells me that as I get further and further away from that 90 degrees, I get less and less area covered with that parallelogram until there's zero area covered when the two vectors line up. Okay? So if we want to multiply this 1/2 by the area of that parallelogram, we have r, the position vector between the sun and the Earth, cross velocity dt, this other length here. Okay, so what we're going to do now is bring that dt out back, because time is a scalar, right? Time doesn't have any direction other than the one, either backwards or forwards. And we're also going to divide and multiply by m. Okay, so we took this dt, took it outside of both the cross product and absolute value, and then we took m divided by m, right? We multiplied by 1 essentially, m divided by m. We kept one of those m's out here, and then we moved the other m through. And the reason then is that this becomes the momentum. Simply our definition for momentum. And now we have 1 over 2m angular momentum dt. So the reason we can get to that is because the definition of angular momentum is r cross p. So we got our p there, we have r cross p, then we have angular momentum, and then we take the absolute value, so the little over arrow thing goes away, and we have the infinitesimal area swept out is equal to 1 over 2m angular momentum times infinitesimal time. Well, we just take this dt and bring it over to the other side. dA dt equals L over 2m. Okay? So this side here, this differential, is the change in area over the change in time. How much does the area change given some change in time? Okay? So the key thing here is now, what is L? Obviously the mass of our object is not going to change in time unless something weird is happening, like it's shedding mass or atmosphere or something like that. So this isn't going to change. Now the question is, does L change? Right? If L changes, then there's no direct relationship between area and time. Right? But if L is a constant, then we know that the change in area with respect to the change in time will itself be constant, and that'll be the same as Kepler's second law: equal areas are swept out in equal times. Okay. So we know that the thing that I wonder if I can fit this all on this board. Yeah. So we know the thing that changes angular momentum is torque. So torque equals R cross F, and we have our Newton's second law for angular momentum, dL dt equals torque. Okay, so if the torque is 0, angular momentum is a constant. All right, so if the torque is 0, angular momentum is a constant, and therefore this is a constant, and then we would have proved equal areas being swept out in equal time. So the torque due to gravity is equal to R, this vector here, cross, and now we need the force, and from that, or rather, from Newton's law for gravity, we get the force. So we just plug in Newton's law for gravity, G big M little m divided by R squared times the unit vector that points in the R direction, right? So that R unit vector is going to point towards the Earth, and of course the force is in the opposite direction of that, okay? Which is why we have the negative sign. But this R vector and this R unit vector point in the same direction. And remember, taking the cross product is like asking the question, how perpendicular are two vectors? And if two vectors are the same, they are not perpendicular at all, so the cross product is 0. So because we have this cross product of the torque due to gravity in a gravitational system is always 0, which means angular momentum is always conserved, right? And now we have in fact proved that equal areas are swept up in equal times. How am I doing on time, speaking of time? We may not do all of gravitational potential today, but we'll at least introduce it. Excuse me. Okay. So now we're going to talk about Kepler's third law and how we can get at that from Newton's law for gravity, excuse me, and other basic physics concepts. This one's pretty quick. So we know the force of gravity, and I'll write again specifically for the Earth and the Moon, or excuse me, the Earth and the Sun, is equal to Gmm over R squared. We also know the force of gravity is equal to mass times acceleration. In this case, the mass of the Earth times the acceleration of the Earth. So this is pretty similar to the calculation we did for the Earth and the Moon. So we'll take that centripetal acceleration, of course, to be v squared over r. We set them equal according to acceleration. We get g m over r squared equals m Earth v squared over r. And then we know that v squared, so just simplifying, v squared is equal to g, mass sun divided by r. And the masses of the Earth cancel out. The only thing that's important is the mass of the sun. And then one of the r's cancels out on each side. And then we also know that velocity, right, this is specifically for the case of a circle, 2 pi r over t. So t squared equals 4 pi squared g mass sun radius cubed. So this is not the full proof for an elliptical orbit, but for a circular orbit, right? So the Earth-Sun system is pretty circular, not perfectly circular, of course, but pretty circular. And now what we get out of calculation using Newton's laws is this constant, right? So when Kepler was writing down his laws, he knew this constant, but just because he was fitting those ellipses to particular periods, so he found this number empirically, but from Newton's calculation, we can calculate it exactly. It's 4 pi squared over the gravitational constant times the mass of the sun. So a really neat thing about this is that if we can observe the period of a planet moving about the sun, and we can find that distance, we can figure out the mass of the sun. Well, that's pretty cool. Okay. So, next thing I'm going to write is just this thing again, but more general. So the force of gravity equals g m1 m2 r squared r half. Okay. So a question you might ask about this law as it relates to how we are accustomed dealing with gravity, which is a vector that points downwards with the same acceleration everywhere on Earth. How accurate is it to use that 9.81 meters per second squared in the negative y direction when we have this guy here? Well, to give you an idea, the radius of the Earth is about 4,000 kilometers. Right? I'm going to look at my paper again to make sure that's true. Oh no, 4,000 miles, excuse me. It's about 4,000 miles. So even a variation by a height of a mile, which is way more than we typically talk about in this class, is not going to be significant compared to that 4,000 miles, especially after the bottom term is squared, right? So what if we're studying situations where this is important? For example, orbits, like we've been talking about, or rockets, right? So we know that, of course, there are many different ways to approach a problem, and we've seen that we can use forces or we can use energy, and then also there's momenta and other additional physics and all the other stuff I talked about during that problem-solving lecture. So when we're talking about things like rocketry, for example, there's two ways we can solve a problem, right? If we want to know how much force or energy does it take to lift an object outside of the Earth's atmosphere and put it in orbits, how much energy does that take? How much force does that take is a very good question if we're interested in aerospace or anything like that. So I used to do that calculation in this class done with forces, back when we were talking about forces, but that was probably the most unpopular lecture I used to give in this class. And it's because the calculation is really difficult. It's a lot of steps. It takes almost the whole class. and it's quite confusing. There's a lot of conceptual tricks involved in it. So I used to do that because now I can show you with considerations due to energy how much easier that same calculation is. How do we find the escape velocity of something we want to put into orbit, right? With Newton's laws, that's quite a difficult thing to figure out. With energy, it's quite simple, relatively. So now instead of spending a whole class doing it the other way, I just tell you how difficult it is, right? And it's in the book, I believe, if you want to go have a look, which I recommend you do, of course. Okay. So, how do we get from this equation to something about energy? Because we just have a force. Well, we know how to turn a force into an energy, right? Because we have our definition of work. So we know that work is going to be some